Welcome to the answer video of the exercise about the production of whipped cream at a dairy factory. We are told that whipped cream is a liquid that can be described by the following power law. The liquid flows through a horizontal pipe to which a pressure gradient is applied. We will start off by making a sketch. The center of the pipe, that line, is where the radius is 0. So horizontal axis will be the x and the vertical axis will be r. So now we define a control volume over dr and dx. What's important here is that you need to remember that the pipe is a cylinder. So if you imagine this problem in 3D, you will not only be working with a prism, but the control volume will actually also be a cylinder that is very, very thin. So now on the left cross section, a pressure P is applied. On the other side, there is a pressure P at the point x plus dx. Closer to the center, the shear stress will be directed towards the right, and closer to the wall, the shear stress will be directed towards the left, because the wall is trying to hold the liquid back from moving. So now we set up a force balance. It's a steady state, so it will be equal to 0. For the pressure force, we multiply the cross-sectional area with the pressure. Since it's so thin, we can just use for the area the product of the parameter, so Tp pi times r, and the thickness dr. So once for the pressure at the point x and once at the point x plus dx. For the shear stress force, we multiply the outside area of the cylinder, so 2 pi r times dx, with the shear stress. And that also once for at the point r and once at the point r plus dr. So now we regroup the terms so that we can rewrite p of x plus dx and p of x as dp, and the same with r times tau. So those terms can be replaced by dp and by dr times tau. Now we divide by dr and by dx and thus find the following differential equation. So now we start integrating. So on the left we find r times tau, and on the right we find minus dp over dx times r squared divided by 2 plus a constant c1. We can now find an expression for the shear stress by dividing everything by r. Now, if we want to find out the sign of the whole term, we first have to look at the different components. So C1 is 0 because the pipe is a cylinder and there's a symmetry around the line R0. And because the pressure is bigger at the entrance than at the exit, dp over dx is negative, and this makes the whole term positive. Now that we have an expression for tau, we can also calculate the velocity profile. I know that in the exercise Vx is given and you're not asked to solve this. However, this integration, even if it is quite complicated, it's something you should be able to do and to solve. So we will do this part of the exercise here as well. First, we need to get those absolute value expressions away. We know that tau is positive from the previous expression, so we can leave the vertical bars away. Next, we look at dv over dr. The velocity becomes smaller when moving closer to the pipe wall, so when the radius increases. Therefore, the term is negative, and the vertical bars can be replaced by a minus. So this is the new expression that we find for the shear stress without the absolute values. So we now have two expressions for tau, and thus we can put them into one single equation. Since we are looking for the velocity profile, we somehow need to isolate Vx. We divide by k and cancel out the power n on the left by raising everything to the power of 1 over n. We then integrate the expression and can isolate Vx. The border conditions here are that at the pipe wall, where the radius is large r, the velocity is 0. Now we need to figure out the integral of r to the power of 1 over n. And note here that I'm going to take out the minus in front of the r by switching the two borders of the integral. We will now fill in all the border conditions, and this will be our expression for Vx that you were given in the exercise. Okay, so now we're on a new page. I'm going to write down the expression for Vx once more. So we have it standing there at the top. And the next thing we're going to do now is to find the expression for the average velocity. This is the expression we're giving for the average velocity. So 1 over pi r squared times the integral of 2 pi times r times Vx times dr. And we will now fill in the expression we just found for Vx. So this will become a very long expression. We can make it a little bit easier for ourselves by cancelling out some terms, so the pi, and we can take the 2 out of the integral. And we can also, in the integral, change this expression by multiplying everything by r already. So then the small r will actually become r to the power of 2n plus 1 over n, because you actually added 1 unit to it. And in this step, we're going to integrate. The first few terms we're all just going to copy and leave them the way they are. And for the integral, the first term, we just look at the small r. So the integral becomes r squared divided by 2. And for the second term, it's more complicated. You add plus 1 to the power. So that would become r over 3n plus 1 divided by n. And now we're going to fill in the border conditions. So we go from the center of the pipe to the pipe wall, which is at the radius r equals big R. As you can see, we're only left with big R's, and we can add those together. This expression can be simplified. The two n plus 1s can be cancelled out, and the 2's as well. In the first term, we also divided by r squared, so we can add that to the power of the big R at the end. So here we have our final expression for the average velocity. We need to compare this with the maximum velocity, which is Vx, where you fill in 0 for r, because the velocity is largest at the center of the pipe, because that's furthest away from the tube, from the wall. And if you divide the maximum velocity by the average velocity, you'll see that all the terms cancel out, except for the ones with the n. So you'll have 3n plus 1 divided by n plus 1. And for the whipped cream, you fill in 0.6 for n, and you'll find that that becomes 1.75. And for a Newtonian fluid, such as water, you fill in n is 1. And here you will find this will become 2. As you can see, the maximum velocity of a Newtonian fluid is exactly double of the average velocity. With the whipped cream, which is a pseudoplastic, this value is lower. So this is it. This was a little bit of a tougher exercise, but I hope you managed, and good luck with the rest.